advantage on the next test. So, okay, here we go. So you have learned about carbonyl compounds in the previous chapter. Sorry, I restarted the iPad but failed to connect the Apple Pencil, so now we're good. You have learned a lot about carbonyl chemistry, but for the most part, our focus has been on the carbonyl carbon as the center of reactivity. The carbonyl carbon has been electrophilic, and then the carbonyl oxygen has been pulling electron density away from the carbonyl carbon. So we've been perfectly fine seeing nucleophiles attack at that carbonyl carbon. One thing we have only touched on briefly, and if you blinked, you missed it, was in enamine chemistry, we did something with the alpha proton. And what we did there seemed unusual, but actually it's the foundation of a lot of things. Protons that are alpha to carbonyls are more acidic than protons, than the corresponding sp3 hybridized carbon-hydrogen bonds, say, in a hydrocarbon. So the pKa of this sp3 hybridized carbon-hydrogen bond is around 50, which is to say never in the history of the universe has water deprotonated that hydrocarbon. On the other hand, the proton that is alpha to the carbonyl carbon has a pKa of 20. So that's a factor of 10 to the 30 times more acidic than a regular sp3 hybridized carbon-hydrogen bond. So the question we need to ask is why? And to do that, we can simply compare the structures of the conjugate bases. And I'll draw in the other CH bonds here. Of course, the conjugate base of a hydrocarbon is going to look like this, with a localized negative charge on an sp3 hybridized carbon. In contrast, the conjugate base of the of the ketone is going to have a negative charge on the alpha carbon. It is true, but you should be able to see that that lone pair on the alpha carbon is adjacent to the carbon-oxygen pi bond, which means I can draw a resonance structure that looks like this, in which the negative charge on the alpha carbon is delocalized and is shared evenly between, well, not evenly, not exactly evenly, but is shared simultaneously between both the alpha carbon and the oxygen, okay? And that intermediate we call an enolate. The reason we call it an enolate is because of something that has come up before in at least a couple different contexts that you might have heard. So this step would involve, to generate the enolate from the ketone, you would have a base simply remove a proton from the alpha carbon to generate this resonance structure with the negative charge on the alpha carbon. By the way, if I had wanted to push arrows to make a pi bond between alpha and carbonyl carbon, and then break this pi bond and move it out onto the oxygen, that would be fine too, because that would just lead to the other enolate resonance structure. If instead, and the reverse reaction of course would be if the negatively charged alpha carbon removed a proton from the base, but if instead the negatively charged oxygen removes a proton from the base and we protonate on that oxygen, we end up with this molecule, which you've seen things like this before. This is called an enol. And what I intend to show you through this is that the ketone is in equilibrium with an enol. Those two are actually isomers of each other. They differ only in the location of a proton, here in a carbon-hydrogen bond, here in an oxygen-hydrogen bond, which I'll draw out more clearly. And they differ in the location of a pi bond, here in a carbon-carbon pi bond, carbon oxygen pi bond in the ketone here in the carbon carbon pi bond. What I'm meaning to show you is that the ketone and the enol are related to each other. The word we use for isomers that differ only in the location of a pi bond and a proton is tautomer. And so we'll use that term. Tautomers differ only in the location of a pi bond and a proton. We'll call this the keto form and this the enol form. In chemistry and in English in general, English is so versatile. We can take nouns like tautomers and we can verb them. So tautomerize means to interconvert tautomers. And then because we're not satisfied with that, we can go ahead and noun the verb we just made and turn it into tautomerization, which is the process of tautomerizing, which is the process of converting one tautomer into another. So you will have heard that word tautomerization before. It came up in the chapter in 351 on alkynes. If you took 351 from me, we probably skipped it because I didn't care. If you took it from somebody else, they probably talked about it. But in general, tautomerization is simply removing a proton to get to a resonance stabilized enolate intermediate and then protonating on the other atom. And so you should be able to go from the ketone form to the enol tautomer or from the enol tautomer back to the keto form. What I will leave for you to sort of practice or try is you can also tautomerize under acidic conditions. So you should give that a try. Try going from the ketone under acidic conditions to the oxonium ion and see whether you can get to, actually, no, that's all there is to it. I'll see if you can push the arrows from acidic conditions to the oxonium ion to the enol. It shouldn't be too hard based on what you've learned on carbonyl chemistry. All right, questions about enols, ketones, and tautomerization? Okay, let's talk about why the alpha proton is acidic in the first place. And the reason for that is twofold. First, when thinking about acidity, you always worry about what is the stability of the conjugate base. And the key reason that the alpha proton is acidic is because the enolate is resonance stabilized. And notice that in at least one of those, in one of the resonance structures, there's this pi bond between what used to be the carbonyl carbon and the alpha carbon. So you would predict if the stability of the enolate is going to relate to this resonance structure that has a carbon alpha pi bond, then you would predict that carbonyls that are more electron poor should benefit more from removing the alpha proton and generating this pi bond, whereas carbonyls that are electron rich should not benefit as much from removing the alpha proton and generating the resonance structure where you've got the carbon alpha pi bond. So we're going to see that if you already know a lot about carbonyl relative stability, then you can already predict a ton about enolate stability and alpha proton acidity. So let's just write down a list of carbonyl compounds that we've dealt with so far. And let's go from least reactive. We'll start, since we're thinking about removing alpha protons, we'll start with neutral molecules. Let's start with an amide. Amides are among our least reactive carbonyl derivatives, carboxylic acid derivatives. There's the alpha proton. And so over here, let's put electrophilicity at the carbonyl carbon. And this is stuff we've already learned in chapters 13 through 16. So pretty low for the amide. At the other end of the spectrum, pretty high for an aldehyde, right? And then intermediate in our sort of list, we had esters were more reactive than amides for sure, but not as reactive as aldehydes. And ketones end up being a little bit less electron poor than aldehydes because ketones have this they have adjacent alkyl groups which can donate electron density into the carbonyl carbon via an inductive effect, whereas aldehydes lack one of those alkyl groups. Okay, so we've arranged these molecules ranking from low reactivity to high reactivity, and I'm talking about electrophilicity at the carbonyl carbon. Now let's look at pKa of the alpha proton. And these aren't numbers to memorize, and you won't need to memorize them. You'll just need to know sort of relative stabilities, and you will see that relative acidities of these alpha protons track with what we'd expect based on how electron poor the carbonyl carbon is. For the amide, the pKa is 30. For the ester, it's around 25. For the ketone, it's 20, and for the aldehyde, it's 17. Now that's significant because we've memorized something back in 351. You memorized that the pKa of water and of an alcohol was around 16. So this means that the aldehyde is not that much less acidic than an alcohol. So you ought to expect bases that are stronger and more basic than an alcohol or an alkoxide to be able to easily remove the alpha proton. Okay, and we can also, if you want, we won't spend hardly any time on this today, but if you want, you can draw the conjugate base, the enolate, of all of these carbonyl compounds and see if you can convince yourself that the presence of this group on the right-hand side is going to affect how stable the negatively charged alpha carbon is. And the way that's going to occur is, remember, the thing that allows us to remove the alpha proton is that the conjugate base is resonance stabilized. That negative charge should be on both the alpha carbon and on the carbonyl oxygen, which I'm highlighting here in pink. To the extent that an adjacent group with lone pairs can also donate electron density into the carbonyl carbon, that's going to interfere with and sort of repel the resonance stabilization of the negatively charged alpha carbon. Okay? So in general, the better electron donating group or the poorer leaving group we have attached to the carbonyl carbon, the less stabilized the conjugate base enolate is going to be, and therefore the less acidic the corresponding conjugate acid will be. And we can reflect that here. I can just say this is the least stable enolate. Whereas this would be a more stable enolate. So hopefully you're seeing how and we've arranged these from low acidity to higher acidity. So hopefully you're seeing how some of what you've learned about carbonyl chemistry reactivity also applies to how acidic the alpha proton is. Questions there so far? Yeah.
basically, like, you see nitrogen and oxygen, instead of having like an inductive effect that you think where they draw away the negative charge, they're adding more electrons, so it's really.
Right. So, yeah, the question is, what is really the effect going on with the nitrogen and the oxygen? There's two things. First, inductive electron withdrawal because nitrogen and oxygen are more electronegative than carbon. But then layered on top of that is a resonance donation effect, which I'll just draw with this arrow here. Nitrogen and oxygen are inductive withdrawers, but resonance donors. And it's not necessarily easy to predict which effect should matter more. For nitrogen and oxygen, the resonance effect matters more. That's definitely true for the stability of the carbonyl compound to begin with, its electrophilicity at the carbonyl carbon. That's also true for the stability of the enolate and the acidity of the alpha proton. Good, what else? Yeah?
What does the enolate look like for the aldehyde?
The enolate for the aldehyde should look like this. And then, of course, for all of these, you could draw a resonance structure that would look like this. And that's true for all of them. Yeah?
So then it's like a thioester. Would that, because it would technically be drawing less electron density away, would it be donating more towards the resonance structure?
Yeah, so if you were to put a thioester here, which thioesters are sort of intermediate in reactivity between esters, they're about the same as aldehydes or ketones. We're not actually going to learn pKa's for thioesters. We will see thioester enolates a little bit later on in chapter, I think, 18. But you would predict them to be somewhere in the neighborhood of aldehyde and ketone enolates for that same reason. Okay, yes?
Just about the drawing, the hydrogen doesn't disappear for the enolate of the aldehyde, right?
The enolate of the aldehyde, what disappeared?
There was a hydrogen on the right, and then on the left, it just looks like.
Okay, for all of these, this is an sp3 carbon. There are 3 protons on that alpha, and over here, there are still 2 left. So nothing, the only thing that happened is one of the 3 protons on the alpha carbon was removed. The other proton on the aldehyde there is not very acidic. And that is because its conjugate base is not stabilized by resonance. Okay, what else? All right, so these pKs are going to be interesting because they're going to help us understand why we're using certain reaction conditions for making enolates. Before we do that, though, I want to talk about some other carbonyl molecules and or enolates, other carbonyl molecules that can also lose alpha protons, which have pKa's even lower than 17. These are interesting because they start to be so acidic that even hydroxide or an alkoxide could completely remove the alpha proton. So we'll start by considering this ester, which has a pKa of 25. What if we modified that alpha carbon so that there are still 2 alpha protons left? But what if we made the third substituent, instead of being a proton, what if we had that be another ester? That's called a diester. Sometimes we're going to pick up this language in this chapter. Here's one of the 2 carbonyl carbons. Here's the alpha carbon. This one's beta to that one. We will call this type of molecule a beta diester. It turns out the pKa for the diester is 13, which means that it's acidic enough for sodium hydroxide or sodium ethoxide to completely 100% quantitatively remove one of those 2 alpha protons. The conjugate, and you'll see why it's more acidic when you draw the conjugate base. So let's just draw the conjugate base in the resonance structure where the negatively charged, where the lone pair is on the alpha carbon. What's the big difference you see between the enolate of the beta diester and the enolate of the regular ester? Two places, right? Two adjacent carbonyls, two places for the negatively charged, for the lone pair on the alpha carbon to go. I'll highlight those here. I will draw one of the two resonance structures. I will leave it to you to draw the other. But you should see how we can easily delocalize the lone pair electrons from the alpha carbon onto the oxygen of the beta ester group and onto the regular carbonyl carbon. And I'll keep the pink highlights on all the atoms. Hopefully by now, when thinking about resonance, you're not thinking about, oh, the lone pair spends a couple minutes here and then hops there and then it doesn't like there and a second later it's up here. No, the electrons are a wave that is simultaneously at maximum amplitude on the oxygen, the alpha carbon, and the other oxygen. And there are nodes in between. Okay, so that's the beta diester. And we can actually do some other things just by sort of mixing and matching groups. So what would you predict for the following two molecules relative to the beta diester? So I'm drawing one here and then one here. We would call this one a beta keto ester because on the beta carbon relative to the ester, you've got a ketone. And then we would call this one a beta diketone. I haven't drawn the protons on the alpha carbon, but that's fine with these structures. They can be implied. All right, tell me what the relative acidities of the beta diketone and the beta keto ester are. Which alpha proton is more acidic? Keto ester or diketone? Diketone is right. Why is that more acidic than the diester? Than the beta keto ester, sorry. Yeah, it's the presence of that oxygen. Remember, the lone pairs on the ester OR group donate electron density into the carbonyl carbon, making it not as electron poor. In contrast, if you want an enolate to be stable, the adjacent carbonyl carbons must be more electron poor. So, in the same way that the ketone is more acidic than the ester, so the beta diketone is more acidic than the beta keto ester. What do you predict for the beta keto ester relative to the diester? Should definitely be more acidic, right? So we can sort of arrange them in this order, and the pKa's get quite low actually. The beta diketone will lose its protons at pHs above 9. All of that's important background for the reactions that we're going to do in this chapter. Okay, anything more you want to say about any of that? Yeah, go ahead.
If we were looking at one of the other alpha carbons there, either on the left or the right, would that just be similar to a ketone?
Right, some of these have other alpha carbons. So this carbon here, oops, I meant to use the orange pen, there we go, is alpha to the orange carbonyl carbon, and yes, you would predict it to have a pK that's close to what's expected for a ketone, around whatever it was, 20? Yeah, because it's only adjacent to one carbonyl. Others? Okay. So now let's talk about ways in which we can form enolates. And I want you to think of two different basic categories for enolate formation. One is what we're going to call reversible enolate formation. What do we mean by reversible? We mean that actually we only form a very small amount of enolate in equilibrium with our ketone or aldehyde or ester starting material. How do we do that? Well, think of it this way. Here is a ketone, and here is a base. Let's actually use an alkoxide just for fun. Somebody went, woohoo. That was a very enthusiastic woohoo. Yeah. Living on the edge with the, so this proton has a pKa of around 20. Over here, the conjugate acid of the alkoxide has a pKa of 16. Chapter 2 question from 351, which side dominates at equilibrium? Left side, starting material, strongest acid loses its protons. Actually, pKa's you can interpret directly to get an idea of what the equilibrium constant should be. Here, it should be something like 1 over 10,000, which means that percentage-wise, at equilibrium, it's 99.99, maybe another 9% starting materials and 0.001% enolate. Okay, that means we don't form very much enolate at all. Now you look at 0.001% and you say that's nothing. What is 0.001% of 10 to the 23 molecules? I don't know, but it's somewhere around 10 to the 20 molecules, which is still astronomically high, right? So that's enough for chemistry to work with. Even a small percentage of molecules can still be a large number of molecules to do chemistry on. So we're going to see that the 0.001 chemistry will be enough to do reactions on enolates. For example, we could react an enolate with some electrophile and have the enolate attack that electrophile and make a new bond. And we're going to do that later. That's called enolate alkylation. But before we do that, we need to make the situation a little bit more complicated, because sometimes the alpha protons are not going to be identical. And so sometimes when dealing with a starting material, we will need to worry about which alpha proton gets removed. Before we get there, let me tell you what I mean by irreversible enolate formation. All we mean by this is we're going to use a base that's strong enough that equilibrium will favor enolate formation by 100%. So here is our same ketone, same pKa of 20. We're going to use a base that looks like this. Negatively charged nitrogen bonded to two isopropyl groups. And it turns out lithium is the counter ion. This is a base that's called LDA, where that's an acronym that stands for lithium diisopropyl amide. And if you ask the question, what is the equilibrium constant between these two, all you need to do is draw the corresponding conjugate acid for lithium diisopropyl amide, LDA. This is called diisopropyl amine, and it has a pKa of 40. So now, 351 question, which side dominates at equilibrium? Strongest acid loses its proton. And actually, if you want, you can do the math, though it's going to involve a large number of zeros. This would be 99.99 out to the 20th place. And this would be 10 to the minus 20-ish %. So basically, at that point, we're willing to round up to 100, okay? So that's essentially 100% or quantitative enolate formation. So you're seeing that depending on the base that we use, a weaker base here, a much stronger base here, we can get either a small amount of enolate or 100% enolate. Yeah?
So when we were doing organolithium reagents, you said that was like the pKa was around the same as like a carbon anion,
Yeah.
which is like what, 30 something? I don't know. Wouldn't that deprotonate that as well?
Yes, so that's a great question. The question is, you've been oversimplified too, right? Because the question has been, before, when you've had a ketone, you've been like, oh, here is an organolithium reagent. I know what to do. Let me attack the carbonyl carbon to get the tetrahedral intermediate, and then I'll do aqueous workup and so on. And now your question is, hold on, the alpha proton was acidic the whole time, and its pKa was 20. The conjugate base of an organolithium reagent, conjugate acid of an organolithium reagent, has a pKa of 50. So shouldn't removal of the alpha proton have been possible there? Yes. Now, why? Why do we see, for organolithium reagents, why don't we generally see alpha proton removal? Two answers, both of them unsatisfactory. The first one is, I told you that life was more complicated with organolithium reagents than originally. I said you could think of them as carbanions, like this, sort of the conjugate base of this acid. In reality, the carbon-lithium bond has covalent character. You're going to hate this even more, but in reality, sometimes you see, do you want it to stop yet? Sometimes you see aggregates of multiple lithiums bonded to multiple carbons. So it's not exactly, and that you might think sterics might make it difficult to do one thing or the other. Presumably that plays a role. The second thing is to consider something that I'm going to show you here that you don't have to write down or worry about, but it's worth knowing. I'm going to just draw a ketone in Spartan, and then we're going to look at the LUMO of the ketone. No, we're not going to look. Oh, no, the Wi-Fi is working. Let's delete and try again. All right, show me the structure, download it. It's still thinking. There we are. Now, an aldehyde you predict, or a ketone, you would predict the LUMO to be the carbon-oxygen pi star, right? It is, but notice there's a little bit of LUMO out on the alpha carbon. Let's just get you, oops, don't look at the HOMO, we don't want to see that. The LUMO is, the HOMO is the lone pairs on the oxygen. The carbonyl carbon is, there's no pointer on Spartan, but there is here, right? Yes. That's the carbonyl carbon, this is the carbonyl oxygen, this is the alpha carbon. Notice that there's some LUMO on those alpha protons. Reason for that we don't need to go into. I'd love to talk about it, but I don't think the juice is worth the squeeze on that particular subject. What it does mean, though, is that a nucleophile approaching a carbonyl in general has to decide, am I attacking at the carbon or the alpha proton? And it's sometimes difficult to predict. We'll try to guide you through that with specific reactions. But in general, think of bases as being able to remove alpha protons. Think of nucleophiles as being able to attack carbonyl carbons. Think of molecules that are both as being able to do both. As an example, notice, I'm going to just, if it's okay, I'm going to erase that horrendousness. You can just pretend that we never talked about that. As an example, this molecule is both a nucleophile and a base. If it acts as a base, it removes the alpha proton. Supposing it attacks the carbonyl carbon, what would we get there? We would get that intermediate, but there's no good leaving groups. And if it got protonated on the carbonyl oxygen, we would then have a hemiacetal, which is not that stable. So yes, we often do have to worry about both reactivity at the alpha carbon and the carbonyl carbon. So far, it's not been an issue, and will come upon times where it will be. All right, other questions? Don't worry about it yet. We're still a ways off from that. Okay, good. So, now, why do we worry about reversible versus irreversible enolate formation? 100% sounds great, so why don't we just always use LDA to make our enolates? First, LDA is pretty expensive. It's air and water. It's at least water sensitive. You have to be careful, and it's quite costly. Sodium ethoxide or sodium hydroxide is quite cheap. So if you can get away with the cheap stuff, why not use it? Second, these two conditions will actually influence what I'm going to call the regioselectivity of enolate formation. So what do I mean by that? So far, the example that I used was on acetone. Regioselectivity refers to when a molecule has more than one alpha carbon and they're not the same. So a simple step away from acetone would be this molecule, 2-butanone, and you've got orange alpha proton here, and then purple alpha proton here. And if we remove purple alpha proton, we're going to get the purple enolate. I'm going to keep drawing the enolate like this, but you are totally welcome to draw the enolate in its other resonance structure form, which has the negative charge on the oxygen. Some people prefer to draw the enolate with the negative charge on the oxygen because they're like, oxygen's more electronegative than carbon, so that resonance structure should be a major contributor. And that's fine. We're going to see that a lot of the subsequent reactions we do with enolates are on the alpha carbon though. So I often prefer just to save myself time and draw the negative charge on the alpha carbon. If we remove the orange alpha proton, we'll get the orange enolate. And of course, we could draw the other resonance structure, which has the pi bond between the orange alpha carbon and the carbonyl carbon with a negative charge on the oxygen. Totally love how I drew that. Okay, I still don't like it. Better. Okay, so those are two possible enolates. Go ahead.
Withdrawing the enolate of pi bond, does cis and trans start to matter?
When you draw the enolate as a pi bond, does cis and trans start to matter? Yes. That can play a role in some reactions. I don't believe it'll play a role in the reactions we'll talk about. Yep, good. Others? Yeah.
I'm assuming like the Zaitsev rules would come into play, that we would see more of the purple.
Okay, Zaitsev rule, which is what?
It's the more substituted alkene.
Okay, you were noticing that the purple enolate has, at least this resonance structure has, the more substituted, by that we mean more carbon-carbon bonds rather than carbon-hydrogen bonds, the more substituted alkene. We'll call this the more substituted enolate, but essentially we're still referring to the carbon-carbon pi bond, whereas this one is the less substituted. I can't spell. There we go. Save myself some time. The less substituted enolate. Yes, that's absolutely true. And because of that, we're going to say that the purple enolate is more stable than the orange enolate. If we were drawing an energy diagram, we would put the purple enolate, which is less stable, say at this energy level. And then we would, I get my left and my right. Did you guys sit there and watch while I called orange purple? Don't stand for that. Isaiah told you in the latter days they would call good evil and evil good. Don't stand for someone telling you that orange is purple. Okay, so the orange one is the less stable one. The purple one is more stable, so if our y-axis or the up and down coordinate represents energy, we would put the more stable enolate there. Okay. So it's true, one enolate is preferred over the other in terms of stability. Now we're going to talk about when stability matters. And it all has to do with the base that we're using, because the base that we're using is going to determine the stability of the starting materials. When we make an enolate, over here we've got the starting material and the base. And then on the left and the right, we have the enolate and then the conjugate acid of the base. So if our base is not very reactive, it's pretty stable, that means, and hopefully you'll forgive me, PDFs don't like it when you span pages. So I'm just going to drag all of that down here. Suppose our base is something that's not very reactive, like F oxide, and then the conjugate acid of our base is ethanol up here with the enolate. Remember, the pKa of ethanol is 16. The pKa of our acidic protons on the ketone is around 20. That tells you it's much more stable to be ketone starting material than to be enolate product if you're using the alkoxide as a base. So let's say this is the energy level of our starting material. And of course, forming the more stable enolate, we would go uphill, pass through a high energy intermediate, your transition state, and then go to the enolate, whereas here we'd go uphill and then pass through a transition state to get to the less substituted enolate. Still, at equilibrium, we're going to have, 99.999% of the starting material. But there's going to be a difference in the amount of enolate that we have. Here it's going to be, 0.001%, and here it's going to be less than 0.001%. I'm not sure how much. The exact numbers are going to depend on the difference in stability between the less substituted enolate and the more substituted enolate. But the punchline is we're going to have more of this one. Okay? Because the enolate's in equilibrium with the starting material, and when a product or an intermediate is in equilibrium with starting material, the only thing that matters is stability. Still going to have way more of the starting material than the enolate, but of your two choices of enolate, the major one's going to be the more substituted one. So when we go on to do subsequent chemistry, it's going to be on this more substituted enolate. Now, next time I'm going to show you how it changes. We're going to keep the enolates in exactly the same place in our energy diagram, but I'll show you how it changes when we use a different base and how that results in a different outcome. All right, good luck on the exam if you haven't already taken it. See you next week.